if I have a circle and a center, the spiral of Archimedes is a curve that looks kind of like that. And the way the spiral of Archimedes is made is that as this radius rotates around the circle, a point on the radius moves outward so that they move at kind of like the same rate. So like over here, I've rotated my circle, my radius a fourth of the way, and this point will be 1/4 of the way. And here I've rotated it halfway, and this point is halfway. This isn't drawn that well to scale, but I'm going to teach you how we can find the area of this weird looking thing. If we have our spiral of Archimedes and we were to split up the circle into, let's say, like a pizza, like into 8 equal pieces, I could make these sectors of a circle, like this one, and then this one, and then this one, and then this one, and this one. And what I have here are 8 sectors of a circle. And those 8 sectors can be added together to find an approximation for the area, and the more sectors, the better the approximation. Let's see how this works with a specific example. Suppose that my circle has a radius of 8. Then when I'm 1/8 through the spiral, I'd be 1 unit out of the 8 on the or 1/8 of the radius. So my first thing goes like that, which means I have this sector here, and the area of that sector is pi times 1 squared divided by 8. Because if it were a whole circle, it would be pi times 1 squared, but it's not the whole circle. So when I get to the second, when my curve hits the second spoke here, and I make this is the actual curve, but I'm making this sector here. That little piece is pi times 2 squared over 8. And this pattern would continue. The third one's here. And if I make my sector there, it would be plus pi times 3 squared over 8. And it would end at pi times 8 squared over 8 when I get to the very last sector. The last sector is actually this whole thing, even though the spiral's kind of going like that. Well, we can factor out a pi over 8, and we end up with 1 squared plus 2 squared up to 8 squared, which is pi over 8 times 8 times 9 times 17 over 6. And from that we can get our approximation. Now more generally, let's just call our circle, let's just call the radius r, and let's cut it into n pieces. The sum of the pieces this very first piece would be over n, because if it was a whole circle, we have to divide by n, because each this little circle would be cut to get this little sector. We have to cut it into n pieces. So we're going to be dividing by n, and the whole circle is pi times r over n squared. And the second one is pi times 2 times r over n, because square, the radius of the second one is kind of double the radius of the first one. And this goes out to pi times n times r over n squared. Well, if I factor out the pi over n, and if I factor out, there's an n squared in every term also, because there's the n in the denominator and it's squared, an n squared there. And there's also an r squared that could be factored out of everything because this numerator has an r. And what's left inside is 1 squared plus 2 squared up to n squared. Let's just move this over here. So what I end up with is pi r squared over n cubed. The sum from 1 to n squared is n times n plus 1 times 2n plus 1 over 6. Now what happens is that this is approximately n, this is approximately n, this is approximately 2n. I'm just going to ignore these plus 1s. They don't matter when n is really large. So the n cubed cancels out with this n, this n, and this n, and the 2 cancels out with this 6. And we end up with pi r squared over 3, which is the area of the spiral. It's exactly 1/3 of the original circle.